Okay. Okay. So what we are going to cover today is basically a, I would say, very hard or stern realization about computability, that most of the problems are essentially unsolvable, undecidable. And some of these problems are also not even recognizable. Okay, so we will propose, not propose, I would say I will just mention two theorems called Rice's theorems. So one theorem says that every non-trivial property of RE languages is undecidable. And the second part says that every non-monotone property of RE languages is not even Turing recognizable. So these three theorems I will prove, and then I will spend a little bit time in showing that despite this very negative result, certain things can still be decided. Okay, so let us formally proceed. So I will first define what is called a property of recursively enumerable languages. To that effect, I will define this thing denoted by capital R, capital E as the languages of all Turing machines. Okay. If you fix the input alphabet like 0, 1, then definitely this is a set. But if your input alphabet can be anything, okay, then actually this is not exactly a set. Okay, so a set cannot be, I mean, consisting of anything. Okay, and that eventually leads to what is called the Russell's paradox and all these things. You may have heard about this, but anyway, for that moment, we can restrict Turing machines over the alphabet 0, 1 or 0, 1, hash, or things like that. Okay. And then this is just not a class of RE languages, it's just a set of RE languages. Okay, so whether you call it class or a set, it's not relevant in what follows. Okay, it's a different kind of mathematical, I would say, argument or setting. Anyway, so by that capital RE, I will imply the collection of all RE languages. Okay. Consider this as a set for a moment. Okay, because everything can be encoded as in 0, 1. So let's say this is a set. And that is how I have written it. A property of RE languages, okay, is essentially a Boolean valued function from this RE. In other words, okay, so how do I specify? I will come to that little later. Okay, fine. Okay, so before, okay, maybe let us do this since. So how do I specify a member of this RE, of this set or class RE? One possibility is I supply a machine, a Turing machine, or more precisely its encoding, and I will say this is the RE language. That is, this is the language of this machine. This is one way of specifying RE languages. Okay. As we have done earlier, this one way of specifying, let's say, regular languages is by proposing a DFA, whose language is that regular language, or by an NFA, or by an epsilon NFA, or by a regular grammar, or for that matter, it can be a regular expression. Okay. Here we have actually two choices. One possibility is by giving a Turing machine whose language is that ARI language. Another possibility which we have seen equivalent to this is an unrestricted grammar. And we will use the encoding of Turing machines instead of unrestricted grammars to specify ARI languages. Definitely we know that given any unrestricted grammar, I convert it to an equivalent non-deterministic Turing machine, and from that NTM I can generate a deterministic Turing machine. Okay. So I will always assume that an ARI language is supplied by or specified by a Turing machine. And also without any loss of generality, we can assume that this Turing machine is deterministic. It may have multiple tapes, multiple tracks in its own, in its only one tape. Things like that we can assume. But henceforth, I will assume that this Turing machine that specifies an ARI language is a deterministic Turing machine, possibly multi-tape. Okay. So this is about the class ARI. That then what a property is. The property of ARI sets is a map from this class ARI to T comma F, T standing for true, F standing for false. Okay. It's just a map. Okay, so I can give you an example to illustrate. So for example, you say that emptiness is a property which is true if and only if the language contains something. Okay. Emptiness. Emptiness is true if and only if the language is the empty set. If it contains anything, the property is false. Okay. And there are some other. Okay, so yeah, this is another issue. Other properties, we will see some other properties, not in this slide, in the next slide, as far as I remember. Then the question is, how many properties are there? As many functions are there from ARI to T comma F. And if I fix something like input alphabet to be 0, 1, then this RE, capital RE, is a set containing how many RE languages? Countably infinite, right? Whereas T comma F is 2. So the number of properties is basically 2 power LF naught, which is actually equal to C, the size of the real numbers, set of real numbers. Okay. Therefore, I cannot specify all the properties. This is first realization, because I cannot specify an uncountable number of things using only a finite amount of space. Okay. So we have to do something about specification of properties. So this is how you will do. I will specify a property by a representative Turing machine, implying that the language of that machine satisfies that property. Okay. So this is a shortcut. So once again, it says that I can specify only countably many properties, although infinite. Okay. But anyway, that's the inherent restriction of, I would say, mathematics or computability. Okay. So only certain properties can be specified, others cannot be. But the way I will specify a property is by a representative Turing machine. For example, if I look at this emptiness property, okay, I will specify it using any Turing machine whose language is the empty set. Okay. So this is something like this. The emptiness property is specified by any member of this set. Take any Turing machine whose language is empty and specify this emptiness property by that machine. Okay. And I would ask questions about this property by querying the machine M, which is a representative of the property. Okay. So I can ask the question whether that machine accepts the empty language or something else. Okay. So properties are specified by any representative member of this set of Turing machines such that the language of that machine satisfies this property. Okay. Yeah. This is fine, right? Emptiness property is specified by any member of or any Turing machine whose language is empty. Okay. And there are some other examples. Finiteness property, set of all finite RE sets. And this is specified by any member of this set of all Turing machines such that the language of M is finite. Yeah. One Turing machine. Because there are actually infinitely many Turing machines whose language is finite. You cannot specify it by all these machines. Yes. How can one Turing machine stand for its entire property class? Once again, I mentioned that there is no other way of doing it. Okay. So it's something like, what should I say? Specify a rational number by one particular rational number. Okay. Something like that. Yeah, so, but this I would say, otherwise we cannot represent properties. Okay. A complete enumeration of that function from RE to P comma F will take infinite space. Okay. In particular, you see that this set is infinite. I cannot specify it that way. So the shortcut is I pick some representative from that set and I will ask a question about that set by asking that particular representative. Okay. So we will soon see some non-examples and then you will understand how it makes sense. Okay. So there are some other things. Regularity property. So you pick context-free property. Now this is something like this, acceptance of a string. So that string in concern in this context is 0101 10000. So the property is that this string belongs to that RE language. So I pick any Turing machine M and its language, or it should accept 01011000, and I take that Turing machine as a representative of this entire class, entire property class. Okay. And one important thing is that this M can be arbitrarily chosen. Okay. So this is how it essentially represents this entire set. So we should not take any assumption on M, except that its language satisfies the properties. Nothing like that it is the Turing machine with minimum number of states, okay? Or something like it is a total Turing machine, things like that, okay? So I will pick an arbitrary element of M, arbitrary element M from this as a representative of this entire property, okay? In that sense, this is good. Okay. If I make no assumption on M, and I ask the question whether the language of M is finite or not. Okay. So it essentially an arbitrary element picked from that set without any strings attached. Okay. So this is a good representative of the whole class. Likewise, you see fullness property, where the machine accepts entire thing, sigma star. Okay. So once again, this is a reiteration of the statement. We specify a property by a single Turing machine, the language of which has that property. And it is an arbitrary member of this set of Turing machines which have this property. Okay. In that sense, that representative Turing machine is good enough because it is arbitrarily chosen from the set of Turing machines whose languages have this property. Okay. So, in that sense, properties are properties of RE sets, not Turing machines. Because that representative Turing machine stands for, I would say, the entire collection of RE sets for which the property evaluates to true. Okay. So that M is a representative. But we are talking about the properties of recursively enumerable sets, not particular that representative. Okay. So this notion will be clear if I go to the next slide. But it seems there is another. A property must be, yeah, independent of the representative machine. Okay. So if we see some non-examples, you will understand this concept better. Okay. So some non-examples. Okay. Consider these properties or this set of Turing machines. M such that M has at least 2022 states. Okay. Now you look at this property of Turing machines having at least 2022 states. Okay. This is not really property of RE languages. Whether a Turing machine has 2022 states or not, or at least 2022 states or not, may have nothing to do with the language it accepts. Okay, for example, you see, we can design two Turing machines, M1 and M2, both accepting the empty set. Okay, so the language of both M1 and M2 is the empty set, which is an RE set. So suppose that I want to represent that RE set empty by a machine. Okay. And I can anyway design M1 to be something like this on any input. It goes from the start state to the reject state and halts. Okay. So you need only three states, S, T, and R, nothing else. Okay. On the other hand, I can design M2 which upon any input will go from S to S1, right? S1 to S2, S2 to S3, S3 to S4, and so on. Okay. And I will somehow, I will make something like 2023 states or whatever you want, 1 million states. And after it reaches that 1 million state, it keeps on looping. It stays there, never moves out, always goes right. Okay. So in that way, it is also rejecting everything. Okay. Now the language is empty. Okay. And if I take that machine M2 as the representative of that phi, okay, what will happen? So as I mentioned, M1 has less than 22 states. It may be just 3 states. And M2 has 22 or more states, maybe 1 million states, possible. Okay. So if the RD set phi is represented by M1, then this property is false. Agree? On the other hand, if phi is represented by M2, this property is true for that particular RD set. Okay. Therefore, which machine will be representative of this thing? That set. We cannot unambiguously choose. Okay, for some Turing machines, this property is satisfied. For some other Turing machines in the same set, this property is not satisfied. So that is the reason I do not call it a property of an RD language, property of RD languages or RD sets. Having 22 states or more or less is essentially a choice of the designer of the Turing machine. It has nothing to do with the language it is going to accept. Of course, there may be certain languages for which whatever Turing machine you design, it is possible that it will have to have 22 states. And for that language, this property may make sense. But it should make sense for any RD set. In particular, for example, phi, sigma star, and things like that. So, this is not an example of property of RD sets. It is a property of machines. Okay. Because the machine may exercise an option of having at least 22 states or not for certain RD languages like phi or sigma star. Okay. And any member of this. Okay. So being a total Turing machine is often a choice for recursive languages. For non-recursive but RE languages, of course, we do not have a total Turing machine and we do not have a choice. So whatever Turing machine we design, it has to be non-total. Okay. But if it is a total Turing machine, we may have a choice. Okay. Whether it will explicitly reject certain strings or go to an infinite loop. Okay. So in that sense, being a total Turing machine is often a property of the machine, not of recursive languages or non-recursive languages. Okay. Because for the same RE language, or for that matter, for the same recursive language, we can have a Turing machine which is total. We can have a Turing machine which is not total. Okay. which machine shall I take as the representative? Okay, for one representative, this property is satisfied. For the other representative, this property is not satisfied. And therefore, this is not a property of Turing machines. Sorry, RE languages. It is a property of machines. Okay. Yeah. Okay. So, likewise, M rejects certain string and halts. So, whether M will reject some string and halt, or will go to an infinite loop for this. This is a choice of the machine. Okay. Not a choice of the, or I would say not an inherent thing. It's a choice of the machine. Okay, similarly, something like this, M ever goes to the right of the input, and M has the least number of states among all machines accepting L of M. Okay. So these are actually certain things associated with Turing machines, not with their languages. And therefore, these are not called properties of RE sets. These are properties of Turing machines. Okay. Okay. So with this understanding, I would.
Sir, hello, sir. Please look at the chat.
Chat. To prove non-property, do we just take one member of the set and one member of the complement and show that they have the same language? Yes. Yes. Yes, precisely. Yeah. Because satisfy this property, some other representative will not satisfy this property. Okay. Yes, exactly so. Exactly so. Okay. Whereas if it is a true property, like M accepts epsilon, whatever representative you choose, it will have to accept epsilon. So the property is that epsilon belongs to the language of that machine. The language contains epsilon. So that is the property. And that is independent of the machine that you choose as a representative. Okay. Yeah. So that's the basic difference between a property and a non-property. Well, okay. So now, as I mentioned, two types of properties that are very crucial in the Rice's theorems, two parts, are so-called trivial properties and monotone properties. Okay. So the trivial properties are defined this way. The constant map, okay, that is true for all RE sets. Okay. And the constant map that is false for all RE sets. These two maps are called trivial, because it is either trivially true for all RE languages or trivially false for all RE. Thing like that. An RE language is an RE language. This is a trivially true property. And the property that an RE language is not an RE language is a trivially false property. Okay. So these two are called trivial properties. Any other property is called non-trivial. What does it mean? That this property is true for some language, for some RE language, one or more, and it is also false for one or more RE languages. Okay. So that is a non-trivial property, which is not universally true, which is not universally false. Okay. So maybe Example of trivial property, as I mentioned, language of M is recursively enumerable. This is universally true. So it's a trivial property. Whereas if I say language of M is recursive, this is not universally true. Because, for example, 5 or sigma star, these are recursive languages. For this ARI set, this is true. Whereas if I take HP or MP, these are not recursive, although recursively enumerable. So this is a non-trivial property. Sometimes it is true, sometimes it is false. Okay. Okay. So then I talk about monotone properties. So monotonicity is with respect to set inclusion. So the monotonicity says that if the property holds for any ARI set L, then if I go to another ARI set L prime which contains L, it will have to be true. Okay, so formally this is the definition. So assume that false is less than equal to true. So that is not exactly very uncommon. False is 0, t is 1. This way you can take it. And whenever A is an ARI set, so A and B are two ARI sets such that A is contained in B, then it says that BA is less than equal to B. So false less than equal to false, possible. True less than equal to true, possible. False less than equal to t is false less than equal to true is possible. Okay. What is only not possible is that true less than equal to false. That is, if the property is already true for A, if you go to any superset, the property will continue to hold. Okay. So these properties are called monotone properties, and any property which is not monotone is called non-monotone. Okay. So here are two examples. So being infinite is a monotone property. Because if an ARI set is already infinite, if you take any other ARI set containing that infinite language, it will have to be infinite. Okay. Similarly, yeah, this is also obvious because A is contained in B. So if A is already sigma star, B will have to be sigma star. Okay. It cannot be something bigger. And if I just look at the other things, being finite is a non-monotone property. Why? Being finite is true only for finite ARI sets. Okay. So what this finite ARI set is contained in an infinite ARI set like sigma star. So for that finite set, this is true, but for that superset, sigma star, this is false. Okay, so this thing is not allowed if we call that property monotone. Okay, so this is a non-monotone property. Likewise, language of M is empty set. This is also a non-monotone property because I can take that A to be empty set and B something non-empty, and A is contained in B. The property is true for A but false for B. Okay, so these are non-monotone properties. Okay, so any other query? Okay, perhaps no. Okay, so what I will now prove is the celebrated Rice's theorem. First part 1, which talks about non-trivial properties. Okay. So it's a very powerful statement. It says that you take any non-trivial property of RE languages, it is not decidable. So no non-trivial property of RE languages is decidable. So if I want to make it precise, I will essentially show that the set pi consisting of all Turing machines n such that the language of n satisfies this property. This set is not recursive. So this set is the entire collection of Turing machines for which the property is true, and I will represent this property pi by a single machine n, and I will ask the question about n. Is the language of n has this property p? Okay, so this is the formalization of representation of properties. Okay. So I have to prove that this set, the set of all encodings of Turing machines for which this property is true, this is not recursive. Okay. So this is the formalization. Okay. So I specify this property by a representative Turing machine and ask whether that satisfies that property, like whether its language is empty, whether its language is regular, whether its language is recursive, things like that. Okay. So this is the first part of Rice's theorem. Every non-trivial property is undecided. Okay. P. Let P be a non-trivial property. And is the property true for empty sets? The empty set is an RE set. Is it true? It may be true, it may be false. And the rest of the proof, I will assume that this is false. Because if it is true, then you just, it's fairly straightforward. Okay. Because in decidability proofs, okay, whether it's a reduction from HP to that language or HP to the complement of that language, it doesn't matter. Okay, so this is false. If it is true, it's basically a reduction to the complement of pi. But that doesn't matter. Okay. So I will assume that this property does not hold for something like the empty set. But now you note that this is a non-trivial property. So there must be a or an RE set for which this property is true. It cannot be universally false. Okay. So by this assumption of non-trivialness, there must exist some RE language L. Of course, it has to be non-empty, such that the property of L is true. Because the property of phi is F, L cannot be empty. Okay. That's a uniquely defined function, a property. Okay. As that P of L is true. And since L is an RE language, there must be a Turing machine whose language is L. It may be a total Turing machine, maybe not a total Turing machine. That is of no concern to us. Okay. Now we make a reduction from the halting problem to the property problem pi. Okay. Is it clear? Okay, maybe in the next line, if this is, you just do this. If this is actually true, then take K, there must exist some L for which this is false. So, and it has some Turing machine K, whose language is L, non-empty, and property of L is false. This will give a reduction from HP complement to pi or HP to pi complement. Either way, we prove undecidability. Doesn't matter. Okay. So it's a reduction from HP to pi. So the input of this reduction algorithm is a pair of encodings, M and W. M is any Turing machine, W is an input for that. And output is a Turing machine N, okay, such that if M halts on W, then that machine N satisfies this property. And if M does not halt on W, then the corresponding Turing machine N has a language which does not satisfy the property. Okay. So Turing machine N is the output of this reduction algorithm such that the language of N satisfies this property if and only if M halts on W. Okay. So this is a very similar looking reduction that you have already seen. So forget V, simulate M on W. If M accepts, okay, not very typical because I have to go for L. Okay, okay. So I will do it little differently. Yeah, because L has to be in the picture. It's not always phi and sigma star. On one case, the language will be phi. On the other case, the language will be that L. Okay, it's not phi, sigma star. Because for sigma star, this is again false. Possible, right? We have to somehow bring that L into this reduction. Okay. So for the moment, remember V by copying from the first step to some second step, third step, something like that. Maybe a second step. Okay. And on the first step, you simulate M on W. W we copy from the finite control, simulate M on W. If the simulation does not halt, this machine N is stuck in this second phase. It is never going beyond the third phase or something like that, whatever follows. And therefore, it will never have an option to accept V. Okay. So one part of the theorem is already satisfied. If M does not halt on W, the language of N will be the empty set. Happy? And we have assumed that the language of that empty set is, rather than the empty set does not satisfy the property. Okay. Otherwise, somehow we have to bring that L into picture. Okay. So suppose the simulation halts.
Sir, run as K. Like N will run similar to K and on V.
Yes,
That should work.
Yes, yes. If the simulation halts, the machine will simulate K on V because V is remembered somewhere else. So V may once again be copied back to the first step after it is completely erased. And then this machine will simulate K on V. And this simulation is just a blind simulation. If K accepts, accept. If K rejects, reject. If K loops, loop. Okay. This is a blind simulation. So accept if and only if K accepts V. Okay. So you see that if M halts on W, then this step finishes in finite time. This copying state is definitely finishes in finite time. This also finishes in finite time. After that, this machine N essentially becomes the same as K. So whatever K does, N also does. In particular, the language of N will be the same as the language of K, which is L. And we know that L satisfies the property. So P of L is true. On the other hand, if M does not halt on W, the machine never comes to the third stage and simulate K. Okay? Because it is stuck in the second stage. So it accepts nothing. So the language of N will be phi. And we know L satisfies the property, the empty set does not. Okay. So if it is the other way, I will have this is F, this is P. Okay. So that's good enough for undecidability proof. For semi-decidability proof, this is not good. Okay. It has to be. Yeah. So that's it. That's the proof. Okay. 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 So what is the time? Okay, fine. Okay, so that concludes Rice's theorem part 1. And the applications are something like all the non-trivial properties that we have seen, whether the language of a machine is finite, contains epsilon, whether the language is context rather regular, whether the language is context free, whether the language is context sensitive, whether the language is recursive. These are all non-trivial properties of RE sets and therefore undecidable by Rice's theorem. Okay. But whether M halts on one or more strings, this is not exactly a property of the RE sets. Rice's theorem says nothing about those properties of Turing machines. It says only something about properties of RE sets. Okay. Yeah. So that's it. Okay. So now let us come to monotone properties, or more precisely, non-monotone properties. Now, this is once again a very strong assumption and strong, I would assertion. It says that any non-monotone property of RE sets or RE languages is not only undecidable, it is not also semi-decidable. Okay. In other words, if I write it in this form, consider the set of all Turing machines for which the property is true. And if I consider this set as pi, name this set as pi, then this set is not even recursively enumerable. Okay. So this is the same as the previous thing, previous statement. The difference is that this property was considered non-trivial. Now this is considered non-monotone. And the conclusion is, earlier it is not recursive. It is here the conclusion is it is not even recursively enumerable. That is the only difference. Otherwise, formally stated, it is this. And I will give an arbitrary Turing machine N and ask whether its language satisfies this property or not. And since this is not recursively enumerable, no Turing machine can answer this question. Okay. Even if we allow non-total Turing machines. Okay. So a proof similar to the previous one should be presented. First of all, what does non-monotonicity imply?
So
There is some,
non-trivial. Non-trivial.
non-trivial is definitely true, but that will prove it is not recursive. Or I need to prove a more strong, a stronger statement. It is not only recursive; it is also recursively non-enumerable. Okay.
So it is true for a subset of something and it is false for the whole thing.
For something superset.
Yes.
Yes. So since this is a non-monotone property, we must have two Array sets, L1 and L2, such that L1 is contained in L2. The property holds for L1, but it does not hold for L2. The definition of non-monotonicity immediately implies this. Okay. There must be Array sets L1 and L2. L1 is contained in L2. Actually, L1 is strictly contained in L2. Thus that the property holds for L1 but not for L2. Okay. And then you have the standard thing. There exists a machine K1 whose language is L1. You have a machine K2 whose language is L2. Okay. So you can take any Turing machines K1 and K2 whose languages are L1 and L2 respectively. Okay. Now I will supply a reduction from complement of HP to pi. Okay. And this reduction algorithm, we will make use of the input M and W for HP complement. And also since K1 and K2 are fixed machines, it will also use this K1 and K2. And all this information can be stored in the finite control of the machine N. Okay, so K1 and K2 are fixed machines. Okay, independent of the input for N. Remembering K1 and K2 in finite control means keep all the transitions of M, keep all the transitions of K1, keep all the transitions of K2, and use these transitions appropriately. Okay. So this is the reduction algorithm. Input is a pair M comma W or M hash W. I will bring a Turing machine N such that if M does not halt on W, then the language of M, N, will satisfy this property. In fact, as you understand, this language will be L1. L1 satisfies this property. Whereas if M does halt on W, the language of N will not satisfy this property. In particular, what it will be? It will be L2. Right? L1 satisfies this property. L2 does not satisfy this property. So I will use this information about M, W, K1 and K2 to build this N in such a way if M does not halt on W, the language of N will be L1. If M halts on W, the language will be L2. Okay. So this machine, this reduction is little bit atypical. Okay, so what it will do, its given input is V. Okay, so what it will do, it will run 3 simulations in parallel. So it will use 3 tapes or tracks, whatever. And on one track, it will simulate M on W. On another tape, it will simulate K1 on V. And on the third tape, it will simulate K2 on V. 3 simulations will run in parallel. Okay. For example, it simulates one step of M on W. Then it goes to the second tape, simulates K1 on W, V. Then goes to the third tape, K2 on V. And all these things, 3 things actually can run in parallel. If that machine has 3 independent read-write heads. Okay. So run 3 simulations in parallel. One step of it in round robin fashion or independently. So K1 on V on the first step, K2 on V on the second step, and M on W on the third step. This is perfectly possible or doable. Okay. Okay. Then accept if and only if one of the following 2 conditions hold. So what is that? K1 accepts V, you immediately accept. Or M halts on W and K accepts V. This is the trickiest part of this reduction. Okay. If K1 accepts V, you always accept. Otherwise, even if K1 does not accept V, but you see that M has halted on W and K2 has accepted V, then also N accepts V. Okay. So then let us see that this condition, this output requirement is fulfilled. Okay. So assume that M does not halt on W. Then condition 2 is never true. So N accepts V if and only if K1 accepts V. Right. If M does not halt on W, then 2 can never be true. So N accepts V if and only if this step 1 is true, the condition 1 is true. So the language of N and language of K1 will be in that case the same. Okay, so M does not halt on W implies N can only accept by condition 1, which is L1, and we know that L1 satisfies the or has this property P. Okay. On the other hand, if M halts on W, then N accepts if either K1 accepts or K2 accepts. Because this is now true. M halts on W, this is a true statement. So it is the language of N in that case will be the set theoretic union of the language of K1 and the language of K2. But the language of K1 is L1 and the language of K2 is L2 and L1 is a subset of L2. So the union is equal to L2. Okay. So if M halts on W, N accepts if either K1 accepts in 1 or K2 accepts in V, So language of n will be the union of the language of K1 and the language of K2. This is L1, this is L2, but L1 is contained in L2, therefore the union is L2. And we know the property is false for L2. So this is an appropriate reduction.
Sir,
Yeah.
instead of doing these in parallel, can we just first run K1 on V? And if it accepts, then it is accepted. Else, if it halts, we run M on W, and
No,
then
no,
we run
no,
K2
no.
on V.
There is a problem. If you first want the first simulation of K1 on V to finish and then go to the other simulations, the problem is that the language of okay, so you are first doing this
Yes, sir.
simulate K1 on V, right?
Yes, sir.
If that simulation halts,
If it accepts and halts, I accept.
yes,
And if it rejects and halts, I go to M on W.
yeah, but if K1 loops,
Nothing gets accepted. I mean, it doesn't get accepted. It just loops.
so the language will be empty, right?
Like V will not get accepted, but other inputs will get accepted.
Okay. Other inputs. The language is always L1, right? No,
Yes,
not
sir.
exactly L1. Uh, what will happen? That
Like L
particular.
L1 will get accepted on like the K1 on V step, and anything which is not in L1 will not be accepted in that state. And if it halts, we go to M on W, and then on K2 to wait. It can get
Okay, so
accepted.
you write down it properly. So,
Okay.
if you, of course, I didn't mention that this is the only way of doing it. So,
Yes, sir.
certain sequentialization may also work. But one thing is what is not clear is that uh, how you enforce the condition of M halting on W or not. Okay, there may be other ways. You just if you can work out, do it.
Okay, so there is a loophole. Like if something is in L2 and it does not halt on
So,
K1. So yeah,
yes.
yeah,
So if
there is a
K1 does not halt on V, then the K2's behavior on V conditioned to the halting of M on W. This is not exactly coming into picture.
yes, sir. Got it. Okay, sir.
So you think about that. Okay. Yeah. Okay. There are other possibilities. Yes. K1 and M in parallel, and then if something happens, M halts, then you simulate K2. Yeah. That you can do. Okay. You can do some minor variations of this, but anyway, this is fine enough, good enough. Okay. So I think that's all about Rice's theorem. If I, for example, want to look at some applications, tell me a non-monotone property, maybe being context-free. Okay. Because you take any context-free language, or I would say not like that. So you take a non-context-free language like WW. Okay. For this, the property is false, but this contains, for example, phi. Okay. Or any finite subset of that WW language, which is even regular. So context free. So for that language, for that finite language, phi or that whatever, that is true. But the WW, this is false, which is a strict superset. Therefore, whether the language of M is context free is not even semi-decidable. And what about the complement? So once again, take this WW. Okay, so whether I am asking the question whether the language of N is not context free. So take WW, for which now this property is true, and it is contained in sigma star, for which the property is false. So being context free is a non-monotone property. Being non-context free is also a non-monotone property. Okay, so both these things are not semi-decidable. Okay. Now, of course, there is an interesting question. Here I am specifying languages by Turing machines. If I specify context-free languages by context-free grammars or PDA and ask similar questions, okay, like whether the grammar accepts anything at all or generates anything at all, generates everything, okay. So are these questions decidable or semi-decidable? Okay. So anyway, so these are different questions. Now I am specifying everything by Turing machines. Okay. And in last 2 years, we were able to cover that little bit on decidable or undecidable properties of context-free grammars or context-free languages. This time we do not have any chance because it's already too late. Anyway, so I will take a little bit of break, and after I come back, I will tell a little bit on things that are actually decidable. Okay. So almost everything about RE sets is undecidable. Okay. Except those trivial things. But some properties may be properties of Turing machines also. Okay. And those properties may be decidable, may be undecidable, maybe even semi-decidable. Okay. This Rice's theorem cannot help you there. So you have to supply specific reductions for proving undecidability or unsemi-decidability, or if that property of Turing machines is decidable, then you have to go and build a Turing machine, a total Turing machine which accepts. Okay. So some such examples of decidable properties of Turing machines, not of RE languages, is what I would just cover for the rest of this class today. And this is fine. So it will take half an hour or so. It's not so difficult. So I will just take a small break and come back. Hello, I am back. Okay. So in the next few minutes, I will give you a set of questions about Turing machines that can actually be decided. And these questions do not fall under the scope of Fries' theorem because these properties are properties of Turing machines, not of their languages. Okay. So once again, let's investigate that issue. The property that we are talking about are the properties of RE sets or Turing machines. Okay. So if I, for example, take this property. Okay, properties are anyway specified by Turing machines, so it is good to understand whether we are talking about properties of their languages or properties of them. So this is our property first, property number 1, whether n accepts epsilon. This is actually a property of RE sets. So this question is whether epsilon belongs to the language of M. Okay. So this property is the property of RE sets, and it can be specified by any member of this, any Turing machine whose language contains epsilon. And this is basically a non-trivial property, right? So this is a non-trivial property. So by Rice's theorem, it is true. It is undecidable. Okay. So undecidable by Rice's theorem, part 1. But this is actually, you can see it's a monotone property. If epsilon goes to some RE set, and if you go to any superset, epsilon will continue to stay there. Okay. Therefore, I cannot apply part 2 of Rice's theorem. So, in order to decide or in order to come to a conclusion whether it is semi-decidable or not, I have to investigate. Okay. So, if it is semi-decidable, then I have to propose a Turing machine for that. Okay. And that Turing machine did not be total. It is anyway undecidable. So I will not design a total Turing machine for it. Okay. Or if it is not semi-decidable, I have to propose a reduction from the complement of HP or something like that. Okay. But in this case, this property is actually semi-decidable. So how you can decide it or semi-decide it? Simply simulate M on epsilon and accept if and only if M accepts. Okay. Yeah. And therefore, if epsilon is in the language of M, the simulation accepts and halts. Whereas, if epsilon is not in the language of M, then the simulation may halt in the reject state or loop. Okay. But anyway, this issue whether epsilon belongs to the language of M can be settled by blind simulation of M on epsilon. Therefore, this is a Turing machine, not necessarily total, for semi-deciding this property. So this language is RE. Okay. It's undecidable, but semi-decidable. Now, if I look at the second question, whether M halts on epsilon, this is something which is not strictly associated with the language of that machine. Whether some Turing machine wants to halt on epsilon or not, it is, I would say, it may be a choice of that machine, not of all underlying RE sets or RE languages which contain epsilon. Okay. So this is not a property of RE sets. So neither part of of Rice's theorem can offer any clue on whether this property of Turing machines is decidable or semi-decidable or neither. Okay. Okay. So epsilon is not in language of M, then upon input epsilon, M may have a choice to halt, that is explicitly reject or implicitly reject by looping. Okay. It has nothing to do with the membership or non-membership of epsilon in the language. Okay. So Rice's theorem cannot be applied. Okay. In fact, what is true is that whether M halts on epsilon is recursively enumerable, but not recursive, and I think we have proved it, right? Maybe we have proved it for whether M accepts epsilon or something like that. Similar type of reduction will do. Okay. RE, of course, is just simulate and accept if and only if the simulation halts. And a reduction from this to this, simulate. If the simulation halts, accept. Okay. So Rice's theorem does not apply here. So we have to do some kind of reduction to prove non-decidability or non-semi-decidability in order to settle this question. Okay. So that's it. Now I will tell a little bit, some 4 or 5 examples of some decidable problems. Okay. And these are all decidable problems about Turing machines, not their languages. Decidable problems or properties of Turing machines. Okay. The first problem is very, very easy. Given the encoding of a Turing machine M, decide whether M contains at least 2022 states. This is extremely trivial, right? This is a decidable problem. You just look at that encoding and find out how many states are there and compare that with 2022. Take a decision. Okay. So this is trivially decidable. Not trivial in that property sense. So, of course, U means a Turing machine will have to decide or semi-decide it. The Turing machine simply looks at the encoding and finds out the answer. And this is definitely a total Turing machine because it's just look at that encoding, find out the number of state, compare with 2022. This can be finished in finite amount of time, irrespective of the input. So this is a decidable property of Turing machines. Then the second example is this: given M, decide whether M halts within 2022 steps on some input like say epsilon. One
Just
second.
blindly simulate it.
Yeah, I will just simulate M on epsilon and for 2022 steps. If it halts by that time, accept, otherwise reject. This is also a very simple decidable property of Turing machines. So simulate M on epsilon for at most 2022 steps. If the simulation halts by that time, accept, otherwise reject. Okay. The machine is also a decider because it's just a limited time simulation of M on epsilon. Okay, so let's now look at a third thing. This apparently does not look like decider. So this says that given M, decide whether M takes more than 2022 steps on some input. Because now a single simulation will not settle this issue. Huh? Even the time sharing thing, that may run forever. That will run forever because there are infinitely many inputs. Okay. So even if for all of these inputs, the number of steps is less than equal to 2022 or less than 2022 or less than equal to 2022, then also you cannot decide this in a finite amount of time because there are infinitely many inputs to consider. Okay. So immediately it is not obvious that this is a decidable property.
So for each step, we'll just check for all of the outputs and all of the things in gamma. Let it be a non-determinate Turing machine, and it checks for all inputs in gamma, like
No, no,
where
no.
it can
Wait,
go.
wait, 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 wait. Uh, what I suggest is that to start with, let us not bring non-determinism in this picture. Okay. So at the very beginning of today's talk, I have mentioned that we will consider M, all Turing machines that we are talking about, as deterministic. Non-determinism has some different issues like whether the tree is infinite or not. Okay. Non-deterministically accepting is not similar to deterministically accepting. More importantly, non-deterministically rejecting is not same as deterministically rejecting. Deterministic rejecting has two possibilities, explicit rejection and implicit rejection. Whereas non-deterministic rejection is a little bit complicated, right? You may have to talk about some infiniteness of the trees and all that stuff. Okay. So better talk about.
So you can take all of the inputs which have length less than equal to 2022. Like it will never go to the right of that.
Yes. So somehow I have to squeeze this search from an infinite space to a finite space. Okay. And I have to take a decision based upon that squeezed search space. Okay. That's the idea. Better not use non-determinism because the issues are a little different there. So this is the relevant observation. M takes more than 2022 steps on some input if and only if M takes more than 2022 steps on some input of length less than equal to 2022. For the second part, you see that the search space is finite. And I can make this simulation because every simulation is a finite step, finite time simulation. I can do this. Okay, so question is why? One thing is obvious. The right side of this implication definitely implies the left side. It's obvious, right? Right side implies the left side. Okay, if M takes some, more than this many steps on some input of length, this is definitely true for unrestricted space. Okay, what about this converse? That this left side implies this. Okay, so this I will prove by contraposition. Okay, so I want to prove the left hand side implies the right hand side of the implication, and I will prove this by contraposition. That is, I will prove that the right side is not true, and I will show that the left side is also not true. Okay. So what does it imply when I say the right side is not true? It says that M takes less than equal to 2022 steps on all inputs of length less than equal to 2022. Then I will show that M takes less than 2022 steps on all inputs. right? So that is the contraposition of the non-trivial part of this proof. Okay. Okay. So m takes less than 2022 steps on all inputs of length less than equal to 2022. So part of that negation of that left side of the implication is already proved. I have to prove it for inputs of size greater than 2022. Okay. And then if there is an input of length greater than 2022, then in order to read that entire input, you need at least 2023 steps. But by the negation of the right side, the machine has halted by that time. Okay, so it never gets a chance to go beyond that 2022th input symbol and take a decision later. Okay, so that's the idea. Okay, suppose that m takes less than equal to 2022 steps on all inputs of length less than equal to 2022, then supply an input of length greater than 2022. M is a DTM. Okay, so its acceptance or rejection or actually halting will come before reading the entire input W. Okay, so that's the idea. But something like this, within 2022 steps, M cannot see more than this many symbols. Okay, and the initial behavior of M on W is the same as the behavior of the prefix of length 2022. And therefore, since M is deterministic, M will halt within 2022 steps. Okay. So that's the basic idea. Squeezing or restricting the search space from an infinite one to a finite one. Okay. So we decided simulate same on all inputs of length less than equal to 2022, each for 2022 steps. That's all. Okay. If some simulation takes more than this, accept, otherwise reject. Okay. So this is the idea. This is something very similar. Given M, decide whether M takes more than 2020 steps, not on some input, but on all inputs. Okay, and this is basically squeezing idea. M takes more than this many steps on all inputs, if and only if M takes more than these many steps on all inputs of length less than equal to 2022. So once again, it suffices to simulate M on all inputs of length less than equal to 2022, each on 2022 steps. Okay. Okay, so this is problem 4. Now, this is, I believe, a little bit more complicated than the previous things. Given M, decide whether M ever moves to the right of the 2022nd cell on input epsilon. Okay. Apparently, the machine may cross this 2022nd cell much later, and apparently this may be unbounded, that time when this will happen. Okay, so some movements are left, some movements are right, some movements may be stationary or left, right, let's say only. Then also right, and then come left, then right, left. The question is it eventually the case that M will move beyond the 2022nd cell? That's not immediately obvious that this is a decidable problem. Yeah, so something like that we have to consider in order to detect a looping pattern. So simulate n on epsilon for some number of steps, and by a clever mathematical calculation you figure out whether, if this condition is not true, then the machine has entered a loop. Okay, so the idea is something like this. Why did I write semi-decidable? It is actually decidable. Oh, okay. This is semi-decidable, simulate n on epsilon. That's true, definitely true. And even if that simulation is infinite, you can do it. But I want to prove that this is a decidable problem. So I have to build a decider for this. Okay, so let m be the number of steps of the machine. K be the number of symbols on the tape alphabet. Okay. What else do I need? State, symbol, perhaps nothing. Suppose that m never goes to the right of the 20/22 cell. Then the head position will be restricted to 0, 1, 2 up to 2022. So 23 possibilities of the head position. Right? And therefore the total number of configurations possible is 23 positions of the head, and the number of states is m. For each position you can have any one of these m steps, and the content of the tape alphabet is k power 2022. Because the 0s cell always contains that constant symbol, left stop, left end marker. And even if I assume that the other things are, anything can be there, the 20/22 cell. So this is the total number of configurations possible. Okay. For these many states, I will see how many configurations, this plus 1. 0th configuration, then first step, second configuration, second step, third configuration, these many steps, this plus 1th configuration. Okay. If by that time the head ever moves beyond the 20/22 cell, I am done. If it is not the case, then some configuration must have repeated by the pigeonhole principle. So that means the machine has entered an infinite loop. Okay, so it will keep on moving in that area of that tape and it will never come out. Okay, so that's the idea. Simulate m on epsilon for these many steps. Okay. If m halts by that time, okay, if the head ever moves to the right of the 20/22 cell, then accept. If m halts by accepting or rejecting without going beyond the 20/22 cell, reject. Otherwise, it has to be the case that the configuration, some configurations is repeated by the pigeonhole principle. So you immediately reject. Thus, the machine must have entered an infinite loop and will never go beyond the 20/22 cell, so reject. Happy? Okay, so that's essentially the thing. And there are some questions. Okay, so this is just summing up slide. So Rice's theorem do not apply to problems specific to Turing machines. Okay, maybe this sentence is not. Rice's theorem do not apply to problems specific to Turing machines, but not to their languages. Anyway, you understand what I mean. So in this case, if I am giving a property of Turing machines, the problem may be decidable. So you have to build a decider, and that may require some kind of arguments like pigeonhole principle or some kind of proofs that I have reported in the previous slides to design a decider. And only thing you have to ensure is that it's a decider that is for all inputs. It must halt after entering either accept or reject state. And the problem may be semi-decidable but not decidable. So that means you design a not necessarily a semi-decider, that is a Turing machine, non-total Turing machine to accept that language. Okay, so design a Turing machine to semi-decide the problem. It has to be non-total because it's not decidable, and then propose a reduction from HP to that thing. Okay. Okay, accept decisions must be infinite amount stuff, and then use a reduction from something like HP. And what about this problem may be even not semi-decidable. So in that case, you have to propose a reduction from a non-RD language like HP complement to that language. Okay. Okay, so this is the only way of settling things. Okay. Rice's theorem theorems do not help you here. So you have to do one of these three things depending upon what kind of language you are dealing with. Okay. So that's the summary slide. Of course, there are some exercises. So we will see. Okay, so this is where I stop. And this is the last class. We will take another tutorial on Thursday, addressing some of this reduction, Rice's theorem, and this kind of issues. And I believe that is good enough. Next week, technically, we will have a class on Monday, perhaps also on Tuesday, because no study leave is declared, right? But let us keep those classes. Of course, if we get some 3 hours or so, we could cover something like some undecidable problems on context-free languages. These things are also interesting, but anyway, let's not worry too much about it. And because we lost, in this class, we lost something like 40 minutes for a power cut. So the other section must have already talked about something called the equivalence of Turing machines with modern computers. Okay. Of course, this is a good thing to know that your random access machines, these are not more powerful than Turing machines. Okay. And some kind of I would say some kind of reasoning for that can be provided. I will upload the slides anyway, but we do not have in this section, we do not have time to cover this. So yeah, so this is where we would like to stop. So see you again on Thursday. And let me tell you one thing, your NSEM is scheduled centrally, the timetable. There is timetable for the central timetable, and that is 12th. 7 to 13, right? 12th. It's again a Tuesday, 11 to 1. Okay. So the timing is fixed, and online and offline tests must be carried out at the same time, of the same duration and all that stuff. That is what the institute recommended, or I would say mandated. So we will most likely take the test in Google form. Okay, so we will let you know about the formalities, what to do later. So that's it. Let us stop today. Okay. Yeah. Okay, of course, if you have a question, let me know. Okay, if not, let us wind up.